Okay, well, welcome everybody, and as you're joining us, so today we're going to have a talk by Professor Elias Khalil at University of Toronto, who will talk about deep reinforcement learning for online combinatorial optimization. So just a brief introduction to Professor Khalil. So he's the Scale AI Research Chair in Data-Driven Algorithms and for Modern Supply Chains at the University of Toronto, and he's a faculty affiliate with the Vector Institute. Before that, he was a postdoc at Polytechnique Montreal, and he obtained his Ph.D. at Georgia Tech, where he was an IBM Ph.D. fellow. That was in 2016. And so his work is in the integration of machine learning and discrete optimization to enable fast and optimal decision-making for supply chain management or supply chain planning and healthcare resource management. So thanks a lot for joining us. We're excited to hear what you've been up to. And yeah, floor is yours.
Great. Thank you, Steve. And thank you to the Waterloo AI Institute for the invitation. So I'll be speaking about this paper we released on Archive about a month ago, which is joint work with Muhammad and Reza, both graduate students at the U of T in engineering. This talk is broadly on the application of machine learning methods for solving discrete optimization problems. And this will be kind of a specific instantiation of that in the online setting, specifically for online matching. And during the talk, feel free to send questions in the chat. I'll try to keep checking if there's something that that's not clear. I'm happy to clarify it on the fly. And then if you have more specific questions, I'll be around for after the talk for the Q&A. Okay, so just to set up the scene and motivate this overall area, I'll start by using the TSP, which is a famous graph optimization problem, just as an example. So you're given, in this case, a complete graph, which is weighted, undirected and weighted. And the TSP asks for a tour, that is a cycle that visits every node exactly once, and that has a minimum cost, where the cost is just the sum of the weights of the edges. In this case, blue edges have cost 1, red edges have cost 2, and so the optimal solution looks like this green one on the right. So you can treat this problem in its kind of original natural combinatorial formulation, which is a common way we're taught algorithms, say in algorithms class. You can also frame it in some constraint optimization language. This could be something like satisfiability or constraint programming, or the kind of framework I work mostly with is mixed integer programming. So these are just general languages that allow you to formulate optimization problems for MIP or mixed integer. In this case, linear programming. You're allowed to use linear equalities or inequalities and a linear objective function, and integer variables, possibly along with continuous variables as well, to model something like the TSP. So what you're seeing on the right are two formulations for the TSP, one in the MIP framework and another in the CP or constraint programming framework. And this could be another way of tackling this problem. This kind of way of formulating combinatorial problems is usually most useful when you're looking for exact solutions. And as you know, this something like the TSP is a very challenging problem, both theoretically and also practically. But we have solvers and algorithms based on tree search that can, solve many large-scale instances in reasonable amounts of time. So that's another kind of part of the typical discrete optimization toolkit. And so putting these things together, the way we typically approach a problem is we go from instance to some formulation. This could be the MIP formulation, or maybe even the original combinatorial formulation, like what you would find in an algorithms textbook. And from that, you might use exact algorithms. In the top, I'm illustrating a branch and bound type algorithm, which is the common approach for MIP and CP. or as illustrated on the bottom, some kind of heuristic approach, like a local search or a large neighborhood search. So what you're seeing here is a step of the 2-opt heuristic for the TSP, which is a famous local search algorithm. And from those, you would get a feasible solution, maybe even optimal, depending on the algorithm and whether you get lucky or not. So that's kind of the typical setting. So this area of research that I focus on deals with machine learning for combinatorial optimization, asking the question, assuming we have access to a data set of instances, similar problems in some way, can we automatically derive better algorithms? And so the reason why this scenario might be interesting is that in practice, for example, if you're using the TSP to model a package routing problem, you would likely not solve one problem in your lifetime in a company. You would solve the same optimization problem regularly. What changes is the data. So this is illustrated in this case for Montreal. You might need to route packages to some customers at 8 a.m. And the traffic conditions at 8 a.m. are different from those at 10 a.m. and so are the customers, and so on and so forth. So essentially, you're solving very similar optimization problems because kind of the road network is not changing really. But for example, the locations you need to visit are changing. The cost of traversing an edge in this road network is also changing as the traffic condition, weather conditions evolve over time. And this gives rise to a data set. And this area of research, which has been, kind of emerging and attracting lots of interest, both in computer science and operations research communities, asks what we can do with this data to improve the solving performance. So you get something like this modification to the problem setting. Now in the top part, there's some machine learning that's done upfront. So you have a data set, you pass it through. In this very simple case, let's say you train some kind of neural network that predicts the optimal tour. You probably wouldn't do this in practice, but this is just for purposes of illustration. Once you have that model, now at test time, you observe some unseen test instances, which you have not seen in the training phase. You do your formulation, either combinatorial or integer programming, and then you go to algorithms. And within the algorithms, this trained neural network can play some role in guiding the search algorithm for an exact procedure or a heuristic, right? So you can imagine, for example, for a local search, a key step is, defining among equivalent actions, which one do you take? Do you act greedily, or do something like simulated annealing that's non-greedy, etc.? There's usually lots of degrees of freedom there that could benefit from some kind of oracle, which is this machine learning model that has seen lots of similar data from the problem that you're interested in. So this is the overall kind of space, and I refer to this survey on the topic, very recent, which covers lots of the literature in the last few years and the different kinds of techniques. So for today, I'm not gonna focus on this deterministic optimization setting or deterministic upfront, offline optimization setting, but rather on an online setting. And so I'll illustrate that with one of the problems we actually focus on, which is EOBM, or edge-weighted online bipartite matching. So in this problem, you have two sets of nodes, U and V. The U set is fixed. Okay, let me say its question here. So does the training data contain optimal solutions? In this figure, I'm assuming that maybe training data contains optimal solutions. So you train like a model that just predicts a tour, but clearly there might be constraints that complicate this process. So there are diverse ways that might either assume access to an optimal solution, or learn through some kind of trial and error, or learn from suboptimal solutions. So in what follows, I will not be depending on the existence of an optimal solution in my training set. I hope this covers it. So in online bipartite matching, we have two sets of nodes, U and V. The U nodes are fixed. So it just, these nodes, they are there up front. And the V nodes come in one by one, and they have edges, which have weights, to a subset of the U nodes. So it looks something like this. Node comes in, now you need to decide whether you match this node to one of the red nodes, so blue to red. Once you do a matching decision, the decision is irrevocable, meaning the red node that gets matched to a blue node can no longer be matched in subsequent iterations. And there are weights. Your goal is to maximize the sum of the weights of the matching. Okay, so standard bipartite matching setting. So let's simulate what a greedy algorithm does for this case. The greedy algorithm at each step picks the edge to the available red node, which has the largest weight. So in this case, we have two options, either weight 4 or 5. Greedy would go with 5. So it does something like this. So now I'm highlighting the edge that we selected. The other one is gone. And you can see we switched or turned off the red node here, just to signify that this red node is no longer available for matching. Second iteration, new blue node comes by. It had an edge actually to the red node that we matched previously. The edge had weight 9, which is higher than what we matched, which had weight 5. But unfortunately, we cannot pick this high weight edge. And a greedy algorithm is stuck with only this one edge with weight 1. So it selects it. Third iteration, similar situation happens, and very nice edge with weight 9 shows up here, but the red node that corresponds to it is no longer available. And so the greedy algorithm has to contend itself with the lower weight edge, which has 1. Now you see all 3 red nodes are turned off. They can no longer be matched. Essentially, the sequence is over, but maybe we have another blue node. It comes in, and unfortunately, we cannot match it. It had a very good edge of weight 9 to one of the red nodes, but all the red nodes are taken. So now we're done. This is the final solution that this greedy algorithm has output, and it has a value or weight of 7, 5 plus 1 plus 1. Okay, so this is the greedy algorithm. The offline optimum, in hindsight, if you knew what this graph looked like and computed just the maximum weight matching using like the Hungarian algorithm, it's a polynomial time solvable problem, you would get this other very different matching. So you see all red nodes are matched to one blue node, and the weights are 9 plus 9 plus 9. So this solution has weight 27. Of course, this is really this is something that's really hard to achieve because this is an online problem. The sequence of blue nodes and their edges just shows up one by one. You don't know them in advance. So the offline optimum is something that you can strive really to achieve, but typically it's going to be very hard to achieve because you might need to be extremely strategic. And you need to really know which edges are going to come later so that you're able to make strategic decisions. But you can compare to it. And so, for example, you could say that the optimality ratio of the greedy algorithm, the online greedy algorithm on the left, relative to the offline optimum in hindsight is 7/27. Okay, so that's what we would call the optimality ratio. And this metric is important in defining evaluation metrics, both in theory and in practice, for assessing the performance of online algorithms. And so here, I'm going to look at some metrics for evaluating online algorithms. On the right, I just have the same illustration from the previous slide. This is the same online matching instance with the greedy algorithm on the top and the offline optimum on the bottom. So the first way is the use of competitive ratio. So the competitive ratio says, what's the optimality ratio? So the value of the algorithm versus the optimal value on the worst possible instance. Okay, so this is really a very worst case metric. So it says, among all possible graphs and among all possible ordering of the blue nodes, the V nodes, what is the worst possible sequence and graph? What's the ratio that you get? Well, we say an algorithm has competitive ratio if we can guarantee that it will never give a ratio worse than this on any instance. So this is kind of very adversarial. It's really a very worst case metric, and it's a very common one for online algorithms. This is one of the main metrics. But clearly, this is, because it's very worst case, extremely pessimistic. So here we're interested in metrics that are kind of closer to what would happen in the real world, not in a theoretical worst case scenario. So getting closer to that, there's a stochastic version of the competitive ratio, which rather than fixing the worst graph, it tries to look for the worst possible generating distribution of graphs. So here what you're seeing is, first we define D as some unknown instance generating distribution. This is the thing that gives you the graph and the weights and the ordering of the blue nodes. And we look at the worst distribution. For that worst distribution, we compute the expected optimality ratio, right? The average optimality ratio. And now you get kind of a slightly weaker type of guarantee, which again, now rather than being competing against the worst case graph, you're competing against the worst case distribution over graphs. Okay. And so here, there's some data generating distribution. We're no longer adversarial. It's kind of similar to how we think about the data generating distribution in like a machine learning type of setting. And so to get there, there's a third version, which is kind of more realistic, closer to how you would like to assess online algorithms that solve similar instances in practice in your real application, which removes the minimization, the outer minimization here, and assumes that there exists some distribution D, which generates the optimization, these online bipartite matching instances that are observed that we need to solve. And we would like to minimize the expected optimality ratio. Okay, and here I give a one paper that kind of introduces this type of metric in a theoretical setting. In this work, we'll be interested in this metric for a more empirical evaluation setting. So this looks a lot like, if you think about empirical risk minimization, it's kind of like expected accuracy or something like that. Okay, so this one we argue is much more realistic, because in the real world, if you're solving online matching, to match users to movies in a recommendation system, or ads to users, or the many, or tasks to servers, or whatnot, maybe you don't need to think about these worst cases, and you assume the data is kind of independently and identically distributed from some unknown distribution, and you'd like to get an algorithm which works well for that. Okay. In contrast to the theoretical computer science kind of approximation algorithms approach, here we'll be interested in not in making assumptions about what the distribution D looks like, but rather saying, we have some data. How do we get something that works well with respect to this expected ratio metric? Okay. Any questions up to here? Okay. And so now I've kind of contrasted two things: the ESP examples at the beginning to illustrate, which was more an offline optimization, just a one-shot optimization setting, versus what I just talked about, which is more online. So those two are clearly different. They have some properties. And I'd like to argue that the online combinatorial optimization setting is very suitable for machine learning. It's a very natural candidate for machine learning for three reasons. Number one, typically in online problems, you have this, because the task is online, you're probably solving it multiple times. Think of some kind of matching problem in a data center or in an online advertisement setting. You're probably solving the online sequence, multiple times a day, once a day, etc. So data arises very naturally, which is good for a machine learning mindset. The theoretical kind of computer science approach of deriving approximation algorithms usually requires lots of assumptions for online problems. So, approximation for offline optimization is, of course, very interesting and challenging, but it's less challenging, for example, than the online equivalent for the same optimization problem, just because online brings with it this inherent uncertainty about what the future is going to bring. And so while for a TSP, you might be, offline TSP, you might be able to design very strong heuristic or approximation algorithm with guarantees, the online counterpart would require you as a theoretical computer scientist to just define or make lots of assumptions about what the data looks like or what the distribution looks like so that you can prove something in expectation. And so this is somewhere where like methods that work well in practice, maybe driven by machine learning, can be of huge value. And then last, online optimization, this kind of sequential decision-making setting fits very nicely with reinforcement learning. And this is something that we will leverage. And so because there's been lots of progress in using reinforcement learning with deep neural networks, giving rise to deep reinforcement learning, which can capture lots of rich information about these nodes in the graph, what they mean, how they're interdependent. This kind of makes it a very nice opportunity. Okay, so moving in that direction, what I'm going to do here is I'm going to formulate online bipartite matching in the reinforcement learning language of Markov decision processes. So I'm going to, again, illustrate the same instance that we saw before. And what you're seeing on the right in this tree is the Markov decision process corresponding to that instance. Okay, so the first diamond that you're seeing here, the one that's colored in red and green, you can think of this as the start state in an episode of a reinforcement learning setting. So some graph and some ordering over the V nodes, the blue nodes, is sampled from this unknown distribution D, giving rise to some instance. And the Markov decision process is going to help us navigate the possible decisions that we make and what kind of rewards we're going to collect along the way. So first, blue node comes in. There's, again, two options, edge to A or edge to B. A greedy algorithm would pick the edge to B with weight 5. In the MDP on the right, these are the same three decisions. I forgot to mention that you have the option in online bipartite matching to skip. So this clearly makes sense. You might want to be strategic and say, I'm not going to waste any of my red nodes in this step because all the edges that are coming to them don't have really good weights. I'd rather just hold and wait till the end. So in every step, you have the decision to either match to exactly one of the edges or to just skip and not match to any edge. So this is illustrated with these dashed arrows in the MDP with the tagline skip to signify that this is one thing you could do. Let's say we didn't do that. We took the action corresponding to the edge to B with weight 5. This moves us to this other state in the MDP. And then next node comes in, we go with C. So same thing happens. We move one step further in this process. This next node comes in. It has edges to C and A. So we take that. And now the red nodes are saturated. So there's nothing to do. And, we've reached, we matched this node with A with weight 1. And we're essentially done. We're in a terminal state. Okay, there's nothing more to do. So this is one path, one sequence of decisions that you could make. And again, it has value 7, 5 plus 1 plus 1. On the other hand, had you done the optimal matching, you would have skipped in the first round and then simply matched the edge with the highest weight, which in this case happens to be 3 edges with weights of 9, and you get the optimal value, which is 27. Okay, so clearly this sequential optimization corresponds nicely to some Markov decision process. It has some interesting properties which are a bit different from the reinforcement learning environments that we usually see. The transitions here are deterministic. You could have a variant of this where the transitions are stochastic, but here we're going to assume deterministic transitions. The rewards of all actions at any step are observed before you make a decision. So, blue node comes in, you observe that it has edges, to these nodes of weights 5 and 2, and so on. So you observe the immediate rewards in advance, which is, in some reinforcement learning settings, you don't really assume that. You assume that you observe the reward after you take the action, the immediate reward. Here, you actually observe it before, so you should clearly use that information to make that decision. The rewards of each step, of each action at a given step, may or may not be state dependent, meaning in this example, no matter whether you in the first step picked B5 or A4, in the next step, the edge to C is going to have weight 1. So here it's not state dependent, but this framework that I'm going to present encompasses other online matching problems where the reward at a given state actually depends on the state itself. It's not exogenous, essentially. It's dependent. And so this is the MDP formulation for online matching, okay? Now, where does machine learning come in, or reinforcement learning come in? At the high level, what reinforcement learning does is it says, okay, I look at the state of the problem. Let's assume we've taken B5 and C1. So we're at the state here, and we're considering whether we take the edge from the blue node to A, which has a weight of 1, or whether we skip. Again, we can opt not to match. So let's say we're considering this situation, we're in this state. Reinforcement learning says, okay, I'm gonna extract some features that represent the state, and I'm gonna run them through some kind of model that's gonna give me scores for the two possible actions. Okay, if you're familiar with reinforcement learning, of course, the scores might be Q values, or in a policy-based reinforcement learning approach, these might be just raw scores or probabilities of taking an action. So it's kind of, it could be either in this high-level schema. But basically, the role of machine learning here, or reinforcement learning, is to train this model to give scores which yield to good solutions, overall solutions, which is the cumulative reward averaged over a bunch of these instances, right? Not a single instances. And this should work, out of distribution, not only the instances your reinforcement learning observes during training. So the main contribution in this paper is to design a bunch of different methods for doing this. Essentially, covering this upper part of the slide, designing, how do we extract features? Do we learn them, or do we engineer them in advance? What does the neural net or the model look like? What does it output, etc.? And also doing so in a generalized way that can fit the many different flavors of online matching. So what would we like a model that helps us match well? What would we like it to satisfy? It should, for one, work for different graph sizes. Okay, so I don't want a model which can only do 3 red nodes. These are the fixed U nodes, because if you're in a data center type of problem, you might have some nodes that drop off, that need to be repaired, some new nodes that get set up, etc. And jobs are coming in, you need to match them. You don't want to have to just have one model for every possible number of machines, or in this case, red nodes. So the model should work with different graph sizes. It shouldn't be tied to any one graph size. It should be permutation equivariant. It's just a fancy way of saying, if I permute the nodes on the left here, the red nodes, if I go from ABC to BCA, and the model originally chooses the edge to A, it should still choose the edge to A when I permute the nodes, right? So this is typical kind of requirement when you have graph structured data. We'll come back to that when we talk about the use of graph neural networks in this setting. But the model should not basically depend on an arbitrary indexing or numbering of the nodes. So that's permutation equivariance here. And I refer you to the deep sets paper for the technical definition of what permutation equivariant means, in case it's just some kind of invariance when the function outputs a vector and not a real value. So you can think of it as permutation in invariance for vector valued functions. Third is that the model should be able to account for history. So this is a sequential process. When I'm at time t, I will have already observed a bunch of edges with varying weights. And so the model should somehow know, how many times have I skipped up to time t in times 1 to t minus 1? What are the statistics of the weights that have been observed in the past? What are the typical U-node degrees? How many edges do they usually have up until this point in time? So the model should be able to ingest that information so that it can guide its decision-making. And last but not least, we would like the model to account for node features. Okay, so I'm giving an example here of a movie recommendation matching problem. So the movies are fixed. They're the red nodes, and users come and go. You see some users repeatedly coming in because they're logging in to the system multiple times a day. You would like to match them to movies so that you maximize, some utility function. I'll give an example of one such utility function. And clearly here, the nodes are not stylized as in the blue-red case. They have properties. So movies have genres, length, actors that participate in them, and so on and so forth, ratings. And the users have their own demographic properties, preferences, etc. So you can think of these as just feature vectors on the nodes. Clearly, such features might influence, the affinity between two nodes, so the goodness of the matching. And we'd like models to be able to take them into account. Note that this is not something that your typical online approximation algorithm can natively take care of. Usually, you don't think about features of nodes in a very clean approximation algorithm setting. So this is somewhere where machine learning and deep learning are kind of uniquely positioned to do something interesting. Okay, so we'll design models that satisfy some of these properties, and we'll move towards models that satisfy all of them at the end. So the first type of model is what we call FF, which is short for feedforward, which is a basic feedforward neural network model. Again, on the left, you have the state of the problem at time t. A new blue node comes in. Let's say it has 3 possible edges with weights 6, 3, and 2. The edge with weight 3 goes to node B, but node B has already been matched in the past. So this node is not available. And there's also the option to skip, as is usual. The feedforward approach says, we'll compute a bunch of features for each of the U nodes, of the red nodes. For example, one feature is, what is the edge weight? Okay. The other feature is, is this node free or not? So you can see that node A has vector 6y for yes, whereas node B has vector 3n for no. So you get, the small vector. Of course, you could have other features. It's just one illustration of that. Each of the red nodes gets its own feature vector, and then we stack them up. We just concatenate them, and we use this vector as the input to one, standard feedforward neural network. Okay, the output layer of this neural network has size equal to the number of U nodes, which again are fixed, so we know how many there are in advance, plus 1, which is the skip, so the option to skip. And in the last layer, it outputs, some scores, some values. So here it's outputting 0.5 for the skip action. So it's recommending that, we don't match this incoming blue node to any of the red nodes. There are a bunch of limitations with this kind of model. Number one, the number of learnable parameters depends on the cardinality of U, the number of red nodes. So this is best illustrated, in the input layer. So you see I need to assume that there are U of these small vectors that I'll concatenate, even though the incoming blue node will probably have edges to only a subset of the red nodes, but this model cannot deal with that variability. And so the number of parameters, this weight matrix in the first layer of the deep neural network, its size is dependent on the size of U. And so when you train it with a certain maximum U in mind over your instances. And so the model is kind of really tied to that. And the same can be said about the output layer, because it needs to output scores for some U. Okay, so there's some dependency here, which is not really desirable. And also, this model is not equivariant to permutations. So if I switch A and B, and I move B to the top and put A second, and I concatenate these features, the way these parts of the vector are going to interact with the weight matrix is not going to be a good way. So the output of the model might differ if I just relabel or reorder the nodes, which is clearly not great. But this is the first kind of baseline type of model that we can use. And again, input is some features of this current state. Output is scores of the possible actions, and consequently, which action are we going to take? So to address some of these limitations, we designed another class of models, which is called Invariant Feedforward, InvFF, which uses the principle of parameter sharing, which is very common principle in deep learning these days. The most maybe famous parameter sharing case is in convolutional neural networks. You have these convolutions moving across an input image. The convolution itself has the exact same weights. You don't have one set of weights for every part of the image. You're sliding the convolution over with the same weights. So you can think of similar ideas for this kind of setting. Namely, now, rather than have a neural network that acts simultaneously on all the possible red nodes, the U nodes, it acts on each of them independently. That's why you see me here repeat the same neural net 3 times, one for node A, one for node D, and one for the skip. Okay, each of these has its own input feature vector. The orange feature here is some context feature, which you see is the same across 3. So for example, here I did average weight of incoming edges, which is 6 plus 3 plus 2 divided by 3. So you get 11 over 3. This is some context feature to tell each of these red nodes what's happening with the other nodes. So we construct one vector per option, per red node or skip, and they all go through the same exact neural network. So same parameters. This is where parameter sharing happens. I don't have one neural network for A and D and skip. It's the same shared network. Each network outputs some kind of score. And as usual, I will take, say, the action with the highest score in the reinforcement learning formalism. So now what we've done is we no longer have a dependency on the number of U nodes, because this model acts independently in parallel, if you will, on each of the possible options. And so this works with any graph size. So you don't need to assume that you have 4 U nodes. You could have 10 U nodes. I would just extend the slide downwards and just run more of the same network in parallel on the additional options. And this approach also has the benefit of being permutation equivariant, meaning the labeling of the nodes, A versus D, if I flip them, D versus A, nothing changes here. Okay, you get the same outputs. We don't care about the identity of the nodes, which is clearly very nice. You want any graph-based machine learning model to not really depend on the labeling of the nodes, because it's irrelevant to decision making. So now we've kind of gone one step further towards satisfying more of these properties that I mentioned earlier, but we haven't talked about history. So the model being aware of where it's at, what has happened up until time step t. So InFFHist augments the model I showed you in the previous slide, extending the feature vector with features that represent basically the history, some aspects of the history. So for example, you might compute the average or variance of the weights for each U node up to time t. Okay, so everything, all these hidden edges that are kind of shown here in the back, if you can see them, their weights matter for decision making, because if you think about it, it might be important to know what the distribution of weights look like, so that if the RL agent observe a very high weight, it knows that this is high because it's high relative to what it has seen before. And so you can design a bunch of features, and we have a complete table of these features in the appendix that I can show later if anybody's interested, or in the paper itself. But basically now you have a kind of a longer feature vector, but the same kind of strategy of using the same network in parallel across all possible actions is still used here. And now we have history that is kind of rich, that's really capturing most of what needs to be known about the state of this online optimization problem. So we're moving up in terms of satisfying properties. The last property, which we haven't really discussed here, is features of nodes in these realistic data sets. So here, graph neural networks can play a role. And this is just a one-slide intro for graph neural nets from our survey on the use of graph neural nets for combinatorial optimization, which is an extensive survey on this specific topic. And for those who are not familiar, a graph neural net is a type of deep neural network which operates on graph structured inputs, like our bipartite graph or this general 5-node graph in this figure. And the typical structure of a graph neural net is this recursion, which says, f of node v4, f, you can think of it as the feature vector of node v4, is equal to, some function of the previous version of this very same vector, and some function of the neighbors of node v4. Here, the neighbors of v4, one-hop neighbors, are v2 and v5. They have their own vectors, and we find a way to aggregate, these vectors and then combine them or merge them with the node's own vector. And we do that in multiple iterations. So you can repeat, this iterative process. So one instantiation of this formula of this update looks like this. So, I look at my neighbors. If I'm node V, I look at my neighbors. For each of them, I look at their own feature vectors. I multiply them by some weight matrix. This is the typical weight matrix that you use for a linear transformation in a neural network. And then I say combine them with some function, linear function of my own vector. This is ft minus 1v, t minus 1 to signify that it's coming from the previous iteration of this deep graph neural network. And then maybe I apply some nonlinearity. So you can think of the sigma as the ReLU or a sigmoid or something, element-wise applied to each entry. And I get my new updated feature vector. Here in this illustration, these blue and orange bar refers to the values in a 2-dimensional vector. So this thing evolves as a function of what my neighbors' vectors look like. And a graph neural net is trained by gradient descent, as you would with a typical feedforward neural net. And what you're training is these weight matrices, W1 and W2. And graph neural nets have the kind of the nice property that they are designed to work on graphs, so they take care of, graph structure, relationships between nodes. And so you get invariance and equivariance to node permutation. So you can relabel, you can basically shuffle rows and columns in the adjacency matrix of the graph. You apply this model, you get the same output for each of the nodes. And the model parameters are shared. These W1, W2, they don't depend on the node. They are reused. So you can apply the same model on a graph which has more nodes or fewer nodes, no problem. And you are learning features rather than the way I was, designing these engineered feature vectors based on our understanding of the problem. As is typical with deep learning, you kind of replace or augment some feature engineering with some end-to-end direct learning. And so you can take this GNN type approach, and you can say, I'm going to apply a GNN to the state directly, to the graph that has been observed. So each of the nodes on the U side gets some kind of vector, and then you can take this vector and turn it into a scalar value, which represents the score as we had before. And now you get a kind of a very flexible model. The most important thing about it is that it can capture the dependencies between the nodes directly. Whereas if you look at this kind of thing, it was treating the nodes kind of as independent and counting on the features to represent statistics that capture dependencies. Whereas a graph neural net, as in typical applications of graph neural nets, is used to kind of encompass graph structure in its own natural design. So this is kind of the most complicated class of models that we can come up with for this type of problem. Okay, so we designed all these different architectures, I'm going to call them, and we can train them with reinforcement learning, gradient descent with some appropriate reinforcement learning method. I'll say which one in a bit. And we can now evaluate the output of this reinforcement learning process, which is essentially an agent, a policy that maps from states to actions. We can compare them to typical online optimization heuristics for online bipartite matching and see whether we are actually learning something from the data which is conducive to a better objective value. So we'll look at two matching problems. EOBM is the same one I've been illustrating, where just edges have weights and you'd like to maximize the sum of the weights of the edges that you select. And a more complicated matching problem, which is online submodular bipartite matching, which you can find in this paper by John Dickerson and co-authors at AAAI. And the movie recommendation problem is inspired by that. So the reward function here, rather than being just the weight of the edge, is some submodular function in everything you've selected or you've matched up to that time. Okay, so a submodular function here is more complex than this just very simple linear cumulative sum that I was showing you for EOBM. So there's some more intricate structure to the problem. The rewards that you get for an action now depend on the sequence of actions that you took up to that state. Whereas in the EOBM, the reward, the weights of the edges were exogenous. They were independent of which actions you take. And so this is a problem with some real applications. For EOBM, we use two synthetic data sets based on generating random graphs from two families and varying the sizes of these problems, the sparsity levels, the weight distributions, etc. And we also looked at two real data sets. One is Gmission, which is a crowdsourcing data set. So you have workers and tasks coming in, and you'd like to match workers to tasks, so to maximize some of weights of the matched edges. And Movie Lens, which might be a familiar data set, which is the movie rating database, and it's used for the online submodular bipartite matching experiments here. So you have movies and users. And you have this submodular reward function that you would like to maximize. And it's based, again, on this paper. So you have 4 data sets used on the two problems. And we use policy gradient methods, in particular, the famous reinforce algorithm, to train this reinforcement learning policy, mainly training the parameters of these different neural network architectures. This is all very kind of modular, very unified. You can just plug in different models on different matching problems, and the same overall training procedure just works. And so, we have some instances which are used for training, others which are used for validation to tune the hyperparameters, for example, of the models, and an completely unseen set of instances, online matching instances. And those are the ones I'm going to show you results for. So everything I show you in the few coming slides is for out of distribution, things we have not seen. And the performance metric, or the main performance metric, is going to be what I showed earlier in the evaluation metric slide, which is the average or expected optimality ratio compared to the optimal value of the problem. And we get the optimal value in hindsight because we generate these instances. We can run an integer programming solver or a maximum matching algorithm to get the true optimum in hindsight. And then we can compare our performance of any algorithm, including these RL-based algorithms that we've designed, to the optimal. And looking at the distribution of this thing that's inside here. Okay, so first set of results is just give you a sense of what these look like. So here we take one data set, which is coming from the Barabashi-Albert graph, which has 100 U nodes, so 100 red nodes, 100 blue nodes. The blue nodes, again, come one by one. So there's 100 steps to this process. And each of the box plots here corresponds to one algorithm. The algorithms left of the white line here are non-learning based. They are greedy algorithms, similar to the one I illustrated before. And the other 5 boxes that you see on the right are these different learning-based architectures that we've designed. The one in green is one trained with supervised learning rather than reinforcement learning. It's something that doesn't work, but that we also try to just make sure that there is value in learning a policy rather than learning, a fixed kind of classifier that just predicts which action to take. And on the vertical axis, you have this optimality ratio. So this is the thing I had here, which is, the value of the algorithm versus the optimum. So alg versus divided by opt, it's something between 0 and 1 because we're maximizing, and higher is better. And we're looking at box plots, so we're looking at distribution of these values on, a number of test instances, maybe I think 1,000 unseen test instances. And you can see here that, the greedy algorithm does something around, median around 0.87. Whereas one of our architectures, this invariant feedforward model with history, does quite a bit better and kind of consistently better on this family of graphs. On this other family of graphs, Erdo-Shreni, here you can think of this as 4 plots. In each subplot, we vary the density of the graph. So the number of edges that appear in the graph. So P here is the probability of an edge in the Erdo-Shreni random graph generation model. So as you move from left to right, you move from sparse graphs on the same number of nodes, 10 by 60, to dense graphs. So there's more edges. And again, the models in blue and orange are the greedy algorithm who's no learning. Everything to the right of them is some learning-based policy. And you can see that the greedy algorithms' performance deteriorates over time. So they get worse as we go, whereas the learning-based methods, as the graphs get denser, become better. So there's a nice interpretation of this, which is as a graph gets denser, then there are more possible edges that you can be strategic about, right? If the node degree is higher, then maybe you should wait until later and match a high edge. So our policies actually learn that, whereas the greedy algorithms, because they are too myopic, they overly eagerly just pick the next edge, whereas they could have waited for the later edges to come, which could have had higher weights. And so we have a nice kind of pattern here. And when we look at realistic graphs from this G-Mission crowdsourcing data set, we also observe good improvements over the typical greedy policies. And we've tried to also understand what is being learned. So what we did in this plot is we looked at whether these learned policies agree with the optimal policy in hindsight. So here higher on the vertical axis means more agreement with the optimal solution, because again, we have the optimal solutions for evaluation. And you can see here that the greedy algorithm, which is in blue, which does not involve any learning, just pick the edge with the highest weight, starts with extremely low agreement with the optimal solution. So less than 30%. On less than 30% of instances, it does something suboptimal, basically. Whereas these learning-based methods, they're somewhere between 60 and 75%. So even though they have not seen the optimal solution during training, they end up doing something which is much more consistent with what you would have done in hindsight. So this gives us kind of some confidence that's what being learned is not really arbitrary. We're learning to act optimally through trial and error by reinforcement learning. And if we look at this online submodular bipartite matching, this is where really the graph neural network, this last gray box here, kind of shines. So here the data set has features for the movies like genres, etc., and for the users like user demographics. And so those are actually input into this model, which makes a prediction about which action we should take. And you can see here that really the gray bar for the graph neural net approaches a ratio of 1, which would have been optimal, whereas the greedy approach is a few percent behind on that. One last thing that we've also looked at among other things in the paper is transferability. So we would like to maybe train these policies on small problems. And if we get a much larger problem in the future, we'd like them to still work kind of well. And so we've looked at that. And here, you can see kind of this heat map of if I train a model from these different families on an instance with 10 U nodes and 30 V nodes, so 10 by 30, and then I test it in each row on potentially something larger. Like I go from 10 by 30 to 100 by 200. So an order of magnitude larger. And here what we're looking at is the average optimality ratio. Same metric as before, 1 means optimal. And you can see that there's really not much deterioration. So I can take this GNN model, train it on 10 by 30, it gives me 0.87. And then I test it on 100 by 100, it gives me 0.85. So not much of a deterioration. So the policies being learned are kind of sensible, it seems, which allows us this kind of generality. And so with that, I'd like to conclude. I invite you to check out the paper on arXiv. We also have the code, which might be useful. And I list here a bunch of activities or tutorials in this space of using machine learning for operations research and optimization. And I'm happy to take any questions now.
Great, yeah, thanks a lot for the talk. If you have a question, we have a little bit of time. You can either type in the chat and I'll read it out, or if you prefer, you can just put your hand up on Zoom, or just, right now, just unmute yourself and say hello and ask a question. I see one hand. Yeah, Said, do you want to ask a question?
Yep. Can you guys hear me?
Yes.
Great talk. Thank you. So my question is,
thank you.
You might have covered it and I might have missed it, but what is the reward that is used to train each one of these networks?
So it's best illustrated here. So let's say we're doing edge-weighted online bipartite matching. So the reward is simply the sum of the weights of the edges that are matched. And we observe that. So we can just use that as our reward signal.
So do you wait until the end to get the sum and then go back and train? And then how much weight do you put on each decision you made on the way?
So that's a very good question. So in this setting, we are faithful to the typical online bipartite matching setting in which each action's weight is observed immediately in that iteration. Now, in terms of training here, we are using the policy gradient approach, which has a way of approximating, the gradient of the reward with respect to the parameters of the model neural network that is guiding this policy. And so it has its own way of, figuring out as it observes, makes more errors and observes more of these reward sequences to kind of optimize the average performance. So we're not making any contributions. They're just kind of reusing off-the-shelf reinforcement learning training methods.
Okay, so it's kind of like a look forward. You look all the way through the end of the episode, and then sum all those. The reason I'm asking is because some of the actions that you make at the beginning, they may give you a reward, but it was a bad action overall in the future. You might, like the example you had, right? How is that captured?
Yes.
In rewards.
Right. So let's say we have a fixed set of instances. During training, these instances will be, we're trying to optimize the average performance of the policy over them. And during training, this policy gradient RL training algorithm will repeatedly revisit these instances, right? And so it's learning as it goes from trial and error. You know, it sees the same instance again. In the meantime, it has probably learned something useful, and it tries to not make those strategic mistakes that you're talking about that it made, you know, in previous training iterations when it saw that instance. But yeah, you do observe the full sequence of rewards, and that helps you guide how you're going to tune the parameters of the neural network that's guiding your policy.
Okay, I guess.
Does that make sense?
Yeah, I mean, we can take it offline. Yeah, I'm going to others ask questions.
Thank you.
Sure. I see Pascal has a question.
Hi, Elias.
Hi, how are you?
Thank you for the nice pedagogical talk. So this was very well done.
Thank you.
So one question I have is when we use graph neural networks to, I guess, embed graphs. So there have been studies trying to see whether we're going to get different embeddings for different graphs, because at the end of the day, I guess if we don't get different embeddings for different graphs, then we might not be able to capture all the information. And that kind of becomes necessary for combinatorial problems, especially if we're solving, let's say, satisfiability problems or other problems like graph isomorphism and so on. So I guess here my question is, I guess you describe all kinds of nice properties of the neural networks, but then to what extent can they capture combinatorial effects? Like you see, if we have, let's say, a node that has several neighbors, in some sense, there could be exponentially many different types of graphs that have that same number of neighbors, and we'd like to make sure that we can capture those features. Otherwise, we're limited, right? So is there something here, like, I guess you haven't really talked about the structure for like doing the aggregation with respect to those nodes, or like the actual architecture of the nets, right? Yeah. Any comments about that?
Sure. So I'll start from the end. In terms of the exact architecture that we use, is kind of a couple steps of like the typical message passing, very similar to what's here on the bottom right on the bipartite graph. And so the first step is encoding, and then each of the candidate U nodes gets its vector, and then there's a decoding stage where these vectors go into some other last network to just give them the actual scores. So it's the pretty kind of basic encoder decoder type of thing. But your question makes a lot of sense. It makes me think that perhaps the first step towards answering is to just think about, can you use a graph neural network to solve the offline version of the problem, just maximum matching, so that we get rid of the dynamic, complicated, uncertainty coming from the dynamic part. There, I think I'm not an expert, but I think there are some results that say if you set up the graph neural network messages correctly, you can emulate. There exists a parameterization that can emulate, basically, that can solve or can emulate any polynomial time algorithm. The maximum weight matching problem here is polynomial time solvable. Then I think, I don't know if we have an architecture which agrees with that, but I think in principle you can have like a universal approximation type of thing for polynomial time solvable problems. Whereas you get the opposite, right? For like something like you were saying, isomorphism, there obviously no graph neural net can represent a polynomial time algorithm, because otherwise it would solve it in polynomial time. But in the dynamic, in the online case, I think things get more interesting. There, I don't know if we can say anything about whether like the graph neural net is going to behave kind of consistently, like the way you were describing it. But that's certainly an interesting question. We have not thought about that, but we will.
Okay, yeah, this is very helpful. So maybe just to be more precise. So for instance, with a student, we were looking at equivariant networks to compute distances, and then so there's a literature on deep sets where you have essentially a set of vectors that you feed in, and then very often, especially for distances, what you need to do is to essentially compute pairwise distances. So there's like a quadratic number of things in principle that you might need to compute. And then in the literature on deep sets, there is there's some initial architectures that were proposed that don't have, like they do their computation in linear time, and sure enough, they completely fail at capturing these types of functions that would require a quadratic amount of computation because they're looking at all pairwise combinations. And here I would think that pairwise combinations would be important for this problem.
Yes.
And therefore, is there something that grows quadratically in the structure of the network? And if not, then what's the magic to capture this, if at all?
Yeah, I think here you don't need quadratic per se. You need to essentially, I think, you need to somehow consider all edges. So we assume this is a sparse graph. So I'm thinking about the offline version of this. Not all pairs of red, blue are available anyway, right? So actually the matching, any matching has size at most a number of U nodes. That's the, because a matching is defined as, you know, each node is matched to exactly or at most one other node, right? So the support of the solution is linear in the number of U nodes. So although you need to think, the model needs to be able to do some combinatorial reasoning, I don't expect it to be difficult here because the graph is bipartite. So the diameter is going to be quite small. So, and you only need to reason in the edges, essentially, not in all possible pairs. So there's some natural sparsity to it here that I think in the offline case, the GNN can probably handle, but I don't know about the online case is trickier. Yeah. And I don't know how to analyze it there.
Okay. Okay, very good. Thank you.
Thank you very much.
All right. I saw we had one last question in the chat. Maybe if we could just take a look at that and then we'll wrap up. So can you see the question there?
Yes.
Maybe
yes.
I'll still read it just quickly because I think if people watch after, then they don't see that. But it says, when comparing FF-hist to INV-FF-hist, less information is given to INV-FF-hist as it is run on independent neural networks. What's the rationale for INV-FF-hist to be better?
Yeah, that's a great question. Yes, so basically the FF models can have more parameters, okay, because they are treating all the red nodes simultaneously. The invariant one, as you correctly noted, treats them independently. So we have to make up for that in designing good features, like this orange feature to give some context. Now, why would the invariant ones work better than the fixed ones? Well, because typically there's no natural ordering to the nodes in the graphs. So you can think of something like this architecture kind of overfitting to a fixed ordering. And really the actual instances are graphs that don't really have any natural ordering. Now, if you make this neural net big enough, maybe that doesn't matter, but typically, you know, have to constrain ourselves to some 2-layer neural net with some fixed number of neurons, etc. In which case this architecture can be too sensitive to how it saw the training data. So that's why in some cases the invariant one, although simpler, can do it just enough to model the intricacies of the problem and work better. But it's not always better. So there are cases where just the feedforward without invariance has enough parameters and it does better. So I hope this covers it.
Okay.
Thank you.
Oh, great.
Thank you.
Okay, so thanks a lot for the talk. Really interesting.
Thank you, Steve.
And thank you everyone for joining and for sticking around for the questions. Yeah, I think we'll wrap up here.